Okay. So hello everyone. Today I'm going to talk about bottlenecks, estimation, and privacy. This work was done together with lots of people. The results that I'm going to present here are a collection of results that were done together with amazing collaborators: Hao Wang, Lisa Vo, Xiang Su, Mike Faria, Muriel Medard, Ken Duffy, Lalitha, Mario Diaz, and Shahab Asudeh. So this is not a talk about differential privacy. Please don't leave the room. I promise you're going to learn something interesting, hopefully. And I'm going to start off talking about the privacy setup that I'll be using today. It's something that we call the one-shot release model. We've seen this in previous talks. And I'm just going to motivate it with an example before I go to the outline of the talk. Okay, so assume that we have the following setting. We have a user, and this user has some data. For example, their TV show ratings that they want to share with a data curator. Okay. Why do they want to share that data? Because they want to receive some utility from that data. For example, recommendations of new TV shows to watch. At the same time, this user has something that they want to keep secret. For example, they want to keep secret the fact if they're a Republican or a Democrat. Well, if the user sends the data as is, they're going to receive the best utility from this data collector, right? The best recommendations. But at the same time, there might be a privacy risk incurred through inferences. Right, the data collector might look at the data and see that this user likes the Colbert Show, likes the Daily Show, doesn't like Fox and Friends. Chances are they are a Democrat. What can the user do about that? They can distort the data, right? They can change the data somehow before releasing it. For example, distorting it through erasures, removing certain TV shows, and release that to the data collector. In this case, they might have a good utility. They might have good privacy. Everyone likes Lost. Everyone likes Friends. Everyone really loves Game of Thrones. But at the same time, the quality of the utility that they receive might be a little bit worse. Right? They might receive a recommendation for a show that's very popular, but they're not very interested in. And the goal of this talk is to understand this privacy utility trade-off from what I call here an estimation theoretic perspective. And I'll make that precise as I go along. Okay? So this is the outline. I'm going to start off with an overview of dealing with this privacy utility trade-off from an optimization framework. This is an approach that you see in a lot of papers in information theory. Okay? And I'm going to explain how this is related to something that we call bottleneck problems. You might have heard, for example, of the information bottleneck. Then I'm going to talk about the chi-square as a privacy metric. I am not making a case to use chi-square as a privacy metric. I'm just going to show that when you measure privacy in terms of chi-square, interesting things show up. Fundamental things show up in terms of the trade-off between privacy and utility. Then present one convex formulation for designing privacy assuring mappings. I might go a little bit quickly through this part of the talk if I don't have time, and go to the end of how can you estimate some of these quantities in practice. Okay? So I'm going to start with a brief overview on bottleneck problems and data processing inequalities and how it relates to privacy within this one-shot release setting that I mentioned. So to make this a little bit more precise, this is a model that we'll be looking at. It's a toy example where we have a private feature S for secret. We have data X. And our engineering goal is to understand what are the limits of designing this blue box here, a privacy assuring mapping that will randomize one sample into a disclosed data Y that you're going to give to the entrusted party. This entrusted party will give you some utility, right? Because privacy without utility is cryptography. And at the same time, this untrusted party will try to infer something about your private feature. And I'm going to make an information theoretic assumption in this talk. And this information theoretic assumption is that we know this distribution here. We're going to relax this a little bit later. But for now, just for the purpose of introducing these metrics, let's roll with that and consider that this distribution is known. So, and the goal today of what I'm going to talk about next is to understand the optimal privacy utility trade-off and try to design mappings that approach this limit. Right? If you give me a privacy metric and a utility metric, what is the optimal trade-off that you can achieve? So in this case, in this scenario, like this hypothetical scenario where the distributions are known, you can do this by formulating an optimization problem. Right? You can formulate something like this. You're trying to design this channel, this randomized mapping, in order to minimize some privacy measures, some privacy risk, subject to some utility constraint. Right? I'm trying to assure that this utility between X and Y is above a certain value, however you may measure it. And today we're going to be trying to understand for different values of privacy measures and utility measures, what are the joint range of pairs of privacy and utility that we can achieve, okay, across all possible privacy assuring mappings. So we want to understand what is the set of these achievable pairs for a fixed distribution P of Sx, okay? So that's what we're doing. So one possible formulation for this, and this was introduced by folks, I've looked at this, Lalita has looked at this, and many others in the literature. You can, for example, estimate privacy as mutual information, right? You might want to minimize the average number of bits between that y carries about s, your secret, subject to some distortion constraints, some square distortion, for example. This is a nice formulation because it's convex and you can actually apply it to real-world data sets and see how these mappings look like. Another interesting formulation that was presented by collaborators of mine is something called the privacy funnel. Okay, so in the privacy funnel, you're trying to minimize the average number of bits, the average information that y carries about s, while ensuring that on average, y carries at least t bits of information about x. And what I like about the privacy funnel is because this is just a specific instantiation of a broader family of problems that I like to call bottleneck problems. And bottleneck problems appear in many places in information theory. Okay, so if you ask what is the joint range of pairs between privacy, the mutual information between S and Y, and utility, the mutual information between X and Y, you can plot this in a graph, right? So here we have this Markov chain relationship, SXY. We're trying to understand the joint range. We're assuming that P of Sx is fixed. On the x-axis, I have the mutual information between x and y. So on the x-axis, I have something that's similar to utility. And on the y-axis, I have something that looks like privacy. So across all possible maps here, this joint range lives within this 45-degree, below this 45-degree line within this blue region because of the data processing inequality, right? So the mutual information between x and y is always going to be greater than the mutual information between s and y. And the truth is that the set of all achievable pairs will live in a convex set that looks like this. Okay, so here on the top axis, I have the stop point is simply when I make x equals y. And on the bottom is when y is independent of x and everything else. So the upper boundary of this region is what is known as the information bottleneck. You might have heard it. It's back in vogue now in terms of neural networks and so on. And the lower boundary of this region is privacy. It's a privacy funnel. Okay, so this upper boundary, this is at the heart of many results in information theory. For example, strong data processing inequalities. When you try to improve upon your vanilla 45-degree line inequality, you have a strong data processing inequality. There's a well-known result in information theory known as Mrs. Gerber's lemma, which is used in network information theory, which is related to the characteristics of this upper bound when S and X are binary. And there's a beautiful paper, I would argue somewhat underappreciated paper by Witzenhausen and Weiner from 1975, where they say many things about the geometry of this upper bound. Recently, and I'm not going to go into details, in a paper at ISIT last year, we said we used the same tools as Witzenhausen and Weiner to analyze this privacy funnel. Then you get the counterpart of Mrs. Gerber's lemma. We called it Mr. Gerber's lemma. For you can fully characterize this region when S and X is binary as well. But you can use the same tools from information, the same tools from convex geometry to analyze that. So another, just to mention this, another thing that's interesting is the derivative of this region right at around the origin. The derivative of this curve, of this upper bound at the origin, is related to something called contraction coefficients. Right? And contraction coefficients are connected to strong data processing inequalities, in this case for KL divergence. And what we're going to be interested in the context of privacy, as I mentioned, is the lower boundary here, right? Because this lower boundary gives you the privacy utility trade-off in the context of mutual information. And I think Kamalika already mentioned F divergences. A natural question to ask here is why use mutual information, right? Why would we use mutual information to analyze this trade-off? We could, in principle, if you're looking at this restricted average case, we could use any F divergence instead of KL divergence, right? And specifically, we will be looking at So what I defined here is something called the F information. You can call it that way. It's basically when you substitute the KL divergence in the definition of mutual information for some other F divergence. And specifically, we're going to be focusing on chi-square divergence. And I'm going to be motivating over the next slides why we're going to be looking at chi-square divergence as a privacy and utility metric. Right? And if you're not familiar with chi-square divergence, it's given by this expectation here. It's just like mutual information minus the log. Yeah.
Could you go back one slide? Just the picture, sorry.
Yeah.
So just to understand, so DP gives you just a straight line, right?
The data processing inequality, yeah.
And this is the actual region?
Yeah, well, this is just a cartoon. Yeah, so this is just the cartoon. The actual region will depend.
But this is the actual region where we're more refined.
Yeah.
I see. So how do you, so what are the variables that control where in the region you are at?
So it would be this, as you change this mapping, this region, you're going to trace this region. As you change this mapping, P of y given x.
Oh, I see. So the only parameter here is PSX is fixed.
Yeah, exactly. P of x is fixed, and as you change the mapping from y to x over all possible y, all over channels.
Because technically you could achieve exactly the straight line if you also change PSX, right?
Yeah, exactly.
You just have to equal that.
Yeah, exactly. But P of sx is fixed.
It's stochastic, and therefore it's not exactly a straight line.
Yeah.
If I wanted to think about this numerically, do I have any constraints on y, or can y like have infinite cardinality?
So you can show that you can. I think the cardinality is call of x plus 2.
Okay, so you can like numerically.
Yeah, you can use your Category business and do that for discrete cases. For continuous cases, it's much more difficult. We have a paper on strong data processing inequalities. I have a paper with Yuri and Yihong for input constrained Gaussian channels. Then you have to use much more heavy machinery to analyze this. But in general, yeah. So we're going to be looking at any other questions before I go on? Okay. So we're going to be looking at this choosing chi-square divergence. It's a divergence that I like a lot. And it's just like mutual information, but without the log. Okay. And just a word of caution, divergences and metrics and average metrics in general do not necessarily provide strong privacy guarantees. Usually you can minimize these F informations just by doing something that looks like an erasure channel. Like you're going to have very little information on average, a leakage on average, but every once in a while you're going to be sending your information in the clear. So I'm not claiming that this should be the metrics that you should be using, but what I'm trying to convince you here is that studying trade-offs within this setting can reveal important facets of the privacy utility trade-off. Okay? So with that caveat in mind, let's move ahead and look at these trade-offs in terms of chi-square divergence. And we're going to be looking at chi-square as a privacy metric. And chi-square divergence is very, very closely related to MMSE, okay, to minimum mean square error estimation. And what I'm going to do next is that I'm going to present to you three different problems, and all of these problems have the same answer. And these give somewhat of an operational meaning to chi-square divergence and something that I call the principal inertia components, okay? So we're going to look at three problems with the same answer. The first problem is a problem of maximizing correlation. So assume that I have a random variable x and you have a random variable y. They're joint distributed according to P of x, y. And by the way, we're just taking a step back now just to look at the operational definition of chi-square. So assume that I have a random variable x, you have a random variable y. These are not necessarily, these could be anything distributed over images or whatever. And our goal is to find functions that have zero mean and unit variance of x and y. I'm going to find a function f of x, you're going to find a function g of y, so that they're maximally correlated, so that they maximize this correlation. If you could solve this problem, the solution for this is something that's known as the maximal correlation coefficient. And I'm going to define this as square root of lambda 1. It's something called the largest principal inertia component, okay? So let's assume we find this solution. We call these maximizing functions f1 and g1, and we repeat the same problem. Right, so now we're finding functions, new function f that's zero mean unit variance and then correlated to the previous one. Same thing for g. Solve that problem again. We get the square root of lambda 2, which we call the second principal inertia component. And we can put that as a constraint again, get the third singular value, the third principal inertia component, and so forth. So these functions that I get as I proceed variationally in this way is something that I'm going to call the principal functions. between x and y. This is useful in something that's related to representation learning. We're going to be talking about this all the way at the end of the talk. And these singular values here are what I call the principal inertial components. So that's the first problem. These principal functions and these quantities also appear as a solution of a second problem, which is a problem of MMSE estimation. So let's go. So let me present this. So the question that we're asking is, which functions of a hidden variable can be estimated with the smallest mean squared error? So I have x, right? And I observe y. And the question that I ask is, what is the function of x, the real valued function of x that has 0 mean and unit variance to avoid trivial solutions, that I can most reliably estimate, that I can reconstruct with the smallest mean square error given an observation of y? If you were to solve this, this function is exactly the principal function from the previous case. It's f1. And the value of the MMSE is 1 minus lambda 1, or the square of the maximal correlation here. Now, you repeat this problem again and say, like, well, what is another function that's uncorrelated with my previous function that I can reconstruct with the smallest mean squared error? So I get 1 minus the second largest principal inertial component. And the solution is f2. And as you proceed like that, you get the remaining principal functions. If you squint at this and look at it from a distance, you can already start seeing that this might be useful for privacy. Right? Because as you proceed through this decomposition, you end up with a basis, right? A set of orthogonal functions for the space of finite variance functions of x. Okay? And you end up with a singular value that tells you how well you can reconstruct any one of these functions. These are nonlinear functions. This is just a basis for the L2 space. So you're going to have a finite number of them if your distribution is over a finite alphabet. You might have an infinite number of them. But then since this is a basis, if you give me any function of x, I can decompose it in terms of this basis. It's a basis, that's the definition, right? And then it gives me a very easy way to decompose not only the variance of f, but also the minimum mean square error of estimating one of these functions, right? So if I can write any function, I can write any function in terms of a linear combination of these basis functions. And then the MMSE, you can really easily write that just in terms of alpha I squared times 1 minus the principal inertial component. Now, this is why chi-square is interesting. Chi-square is interesting because it's the sum of all these PICs. Okay, so you can see that the chi-square is exactly the sum of all these principal inertial components. So if chi-square is very, very small, you have something that's somewhat akin to privacy, right? What that means is that there's no non-trivial function of x that you can reliably estimate from y, because all these values will be very small and the MMSE will be very large. And if this chi-square is high, do you have something that seems like utility, right? That it means that there may be functions of x that you can reliably estimate given y. And we're going to explore this a little bit later.
So for now, there's no privacy also.
There's no privacy yet.
Estimating f1,
yeah.
not estimating f2 again, and so on.
But you can already start getting a feel of how this would map to privacy. Because what we're going to show is that when you're designing these mappings, you want to somehow align your mapping such that only certain functions can be estimated while others cannot.
These are kind of bases.
Exactly. So that's where we're going with that.
So in her context, it's one class of capacity limited adversaries, right?
Well, yeah, you might be able to map it that way, absolutely.
These adversaries are interested in doing MMSE estimate.
Yeah.
But on a large, I mean, I would still guess these Fs have to be on some well-defined space. They cannot be some arbitrary.
So it sounds like, it's very reminiscent of these reproducing kernel Hilberts.
It is. Yes. We can. Yeah. I'm gonna put that question on hold.
Okay.
Because I don't fully understand the connection between the two, but there's definitely a connection. And
the person you might want to talk to is Arthur Breton, who could, he's this guy who does this RKHS, and he can look at anything and make an RKHS out of it.
So, and I think to provide further evidence that this is connected to that, this is the third interpretation, right? So we looked at these principal inertial components in terms of maximizing correlation, looked at it in terms of minimizing mean squared error. And what's really the machinery that's behind this is because what we're doing is nothing more than looking at the spectrum of the conditional expectation operator. So if you give me the space of finite variance functions of y and the space of finite variance of functions of x, I can define the conditional expectation operator. It's just a linear operator that maps a function here to a function in x by taking conditional expectation. It's a linear operator. We can diagonalize it, right? We can look at its singular values. We use this in fairness. Actually, like if you were to the talk, look at the talk yesterday, we talked about local perturbations of probability measures. This is what guides the geometry of those local perturbations. And yeah, and that's what I'm going to say about that. So for the math aficionados in the room, what we're looking at is nothing more than the spectrum of the conditional expectation operator. How on earth would you compute these principal inertia components, right, if I give you a distribution? Well, if your distribution is discrete and finite, right, so if it's over a finite alphabet, you can build a matrix that looks like this. Then without loss of generality, I just assume that things are distributed from 1 to u and 1 to v. I can build a matrix whose entries are the joint distribution divided by the square root of the product of the marginals, take the singular value decomposition of this matrix, and the singular values are exactly the principal inertia components, square root of the principal inertia components, and up to a regularization term, the left and the right singular vectors correspond to the principal functions. There is a statistical method called correspondence analysis that if you give me a data set, they try to build a contingency table and normalize it exactly like that in order to estimate these principal functions. And I'll have more to say about that towards the end of the talk.
One thing, it's also very reminiscent of CCA, canonical correlation.
Yeah, this is almost like a nonlinear CCA.
Aha,
Yeah.
I see.
So,
And then what you could try to do is a kernel CCA.
yeah.
Right? And if you use the right, like the Gaussian kernel or something, the RBF kernel, then you might be able to even show that, like in the limit your function classes are complete. And then you are in an RKHS basically.
I have to think about that more, yeah. So, and here's an equation that you might find interesting. Maybe many of you haven't seen it before. You can think about these principal inertia components as giving you a fine-grained decomposition of the joint distribution. So in the discrete case, if you give me a distribution of P of xy, I can decompose it in this form, where this is independence, right? This is just your, if you had a independent distribution. And the coupling between x and y can be given in terms of the PICs and these principal functions. Okay, so you can do this for many distributions. I was not the one that proposed this. Like, this has been studied in many different places in the information theory, mathematical statistics, and probability theory literature, dating all the way back to Hirschfeld and Gibelin, Sarmanov and Reyni in terms of maximizing correlation. Witzenhausen has also a beautiful paper studying. He appears many times in this talk, but studying this in the context of maximizing correlation and strong data processing inequality. Also Ian Gax and many others. I also want to mention the very exciting work that's happening at MIT by Li Zhongzheng, Greg Vornell, and his team. They are using these principal functions to understand things like transfer learning and so on. Some really cool stuff. This also, as I mentioned, statisticians have been studying these PICs in the context of something called correspondence analysis. That's where I bring that terminology from. You can think about correspondence analysis as the ugly sibling of principal component analysis. But you look at it there. Also, there's a fantastic paper by Buja and also a method proposed by Breman and Friedman called the alternating conditional expectations that seeks to estimate the largest principal inertia component. And if you want to see some of these references, I'll refer you to recent transactions papers that we had from a couple of years ago. So, and our contributions, what I'm bringing to the table here today, is that we're applying the PIC to obtain an estimation theoretic view of privacy. So let's go back to privacy, okay? And now, before we had something that looked like the information bottleneck, where we used mutual information bottleneck. And what we're going to look now is at the estimation bottleneck, where I'm measuring the dependence between x and y and s and y in terms of chi-square. Okay, this is an F divergence, so the region of achievable pair, and just before I say that, let me just refresh your memory. So S will be a sensitive attribute, X is your data, P of Sx is fixed, and we're trying to understand the limits of designing the mapping from X to Y for disclosing data. So chi-square is a divergence. It also satisfies the data processing inequality. The set of achievable pairs will also live in this blue set here, below the 45-degree line. And what I'm going to present next is a proof in pictures of a theorem, which is a sharp lower bound for something that we call the estimation funnel, which is the counterpart of the privacy funnel. Okay, so just bear with me on this. So here's the picture, right? So we have the joint distribution between S and X is fixed. We can look at the PIC decomposition of the joint distribution between S and X, right? And when you do that decomposition, what you end up with is with a set of basis functions of S. And through the conditional expectation operator, right, they're transformed to these functions of X, where each function corresponds to the MMSE estimator of F in this spaces here. So if you ask me, given an observation of X, what is the function that you can reconstruct with the smallest mean square error? The zero mean unit variance function, that will be F1 here, right? And the error will be 1 minus the largest principal inertial component. What is the hardest function in terms of MMSE? That will be FD here. And that corresponds to the smallest principal inertial component. Now, our engineering goal is to understand how to design this blue box here, this privacy mapping, right? So if we're measuring both privacy and utility in terms of chi-square, intuitively, you want to design this mapping such that when you observe Y, the only function of X that you can reliably reconstruct in a mean squared error sense is the one that's aligned with G of D here, which in turn is the MMSE estimator of the function that you can least reliably reconstruct from X. So if you're only revealing a little bit of information about X through Y, you would want to review it in this direction here. This doesn't mean that you're revealing G of D. That means that you're designing a randomization mechanism. You're designing this randomized mapping so that if you observe Y, only G of D can be reliably inferred. We don't know if we can do that exactly. Hence, it's a lower bound. But this gives us the first part of the lower bound of the region for the estimation for the privacy funnel. Now, let's assume that you're walking here and you're releasing a little bit more information about X through Y. The second direction that you're going to reveal this information is the one that's aligned to the second hardest function to estimate in an MMSE sense, FD minus 1. You would like to reveal Y in such a way that, given an observation of Y, the only functions of X that you can estimate reliably is in this two-dimensional subspace given by G of D and G of D minus 1. Again, we don't know if you can design such a mapping, but we can show that this is the best that you could do in theory, hence a lower bound, and that gives me the second part of this region. And as you proceed like that, you get the remaining lower bound.
Flavio, how does the mutual information bill or the chi-square distance between S and Y come into picture here? But that's obviously constrained, right? If I just want to minimize the inference of X through Y, I would just put Y as independent of X.
Yeah, so no, it comes here where we're trying to release at least some amount of chi-square information between X and Y while minimizing the chi-square information between S and Y.
Sorry, the other way around, yeah.
Yeah.
So you constrain, oh, I see. So your set of mapping is constrained.
Yeah, exactly.
So this is really piecewise linear, or is it just your
The lower bound is piecewise linear. It's piecewise linear.
Oh, it is.
Yeah. So the exciting part about this, well, at least the part I get excited about, is the very beginning of this lower bound, right? Because if you can show that the smallest PIC is 0, it means that I can walk in this plateau here without like releasing any information about Y. So that means that I can release some information about X through Y, while keeping S and Y perfectly independent, because chi-square of S and Y being 0 implies perfect independence.
So for me, if I'm doing a deep neural network and if I could somehow figure this out, then I know at least in some basis that's what I should reveal.
Exactly. Well, yeah, if you could learn this, that says like that, and this is an if and only if statement, and gives you the necessary and sufficient condition for perfect privacy. When can I reveal some information about X while keeping S perfectly private? And that's given by the smallest principal inertial component. And you can flip this argument around and you get also a piecewise upper bound for the same region, just using this kind of like water list, kind of like filling out the singular values approach, and for something that we call the estimation bottleneck. Okay, so I think I still have time to go through this. Now I'm going to talk a little bit, how can you use this to actually design privacy assuring mappings? I'm going to give one way of doing it in the case you know the distribution, right? You can actually build this as a convex formulation. And I'm going to illustrate this through a question that I asked the other attendees of this symposium earlier, which is, how can a random variable, if you give me a random variable X, how can it be perturbed in order to hide a single function of X, f of X, right? So let's assume that S is a function of X. How can you design this mapping, produce a Y, a perturbation of X, so that that single function is hidden. And based on what we saw on the principal inertial components, you can see that that probably will play a role here. So just as a warm-up, just as a quick warm-up, let's look at a model that all of us know and love, which is the one-time pad. Okay, so one-time pad, of course, now assume that x is actually a whole sequence of bits, x of n. You're disclosing y of n, and you're restricting your privacy mechanisms to be additive in this way. Okay, so I'm just gonna XOR it with a key, for example. So assume that my key is short, right? So instead of hiding the whole message, my key has entropy smaller than the input of the channel, so I can't hide the whole message. But can we information theoretically hide certain classes of functions, right? Like regardless of the computational power of an adversary, right? Even with a short key. Of course, information will be leaking, obviously, but maybe some things will be information theoretically hidden. And this exercise will serve as a warm-up for a more general formulation. So just bear with me on this. So in this case, if you assume that x is binary, we're going to write binary as -1 and 1. We know from Fourier analysis of Boolean functions, it's an amazing book by Ryan O'Donnell on that we can decompose any real function of x in terms of a basis. This basis is given by the parity bits of the inputs. And these rows here are just like, you can think about those as the alphas we had before. These are just the weights in terms of decomposing your function in terms of the spaces. This is a fact that you can do that for any Boolean function. And in this case, when x is uniformly distributed, it turns out that if x is uniformly distributed and your channel is a BSC, so this key is just it's just bit flips where you flip a certain bit of probability epsilon. The left and right principal functions in this case are exactly these parity bits. Note that here, the entropy of the key can be much, much smaller than the entropy of the message of x of n of the input. But the question that we ask is, given yn, how well can we guess or infer the parity bits, right? And it turns out that for this vanilla binary symmetric channel, the binary symmetric channel acts almost like a low-pass filter, right? So from the output of a binary symmetric channel, you can reliably estimate parity bits of low-order interactions. So each individual bit, you can infer them pretty well. But if you ask me the XOR of the whole sequence, you have a hard time guessing that. And specifically, if you define a function chi of s of x of n as the parity bit of a set cal of s, how well you can guess that bit from the output of binary symmetric channel decays exponentially with the number of entries in that input. So the takeaway here is that the binary symmetric channel acts almost like a low-pass filter. And when the case where x is uniform, we can generalize this analysis for any distribution of additive noise. Here, the left and right principal functions are exactly the parity bits. You can decompose any function, unit variance function, in terms of a weighted sum of these parity bits. And you can write the MMSE of estimating this function, this really nicely, as 1 minus the sum of alpha squared. There's an s missing here, times this expected value, where you might recognize this as simply the Hadamard, the principal functions in this, the principal inertial components in this case are simply the result of the Hadamard transform of the noise. I know there's a lot to unpack here, but what I want you to take away from this is that, well, if we want to hide certain functions of the input, I could potentially tailor this noise in such a way that they kill exactly they attenuate exactly the values of the components where my function, the values alpha of s of the function that I want to hide is high. So again, let me restate this. All that I'm saying is that, well, if you want to design this mapping now to hide certain functions, I can tailor this noise in terms of how I decompose my function in terms of these parity bits. How can we generalize this? You can actually generalize this by building a convex optimization problem. So this is the setup that I'm going to restate the same thing now in a slightly more generality. We return to our privacy setup, right? So S is our secret private feature, X is our data. We're going to assume that what I want to hide is a set of functions of X, denoted by S1 to Sm. And I'm going to restrict the MMSE of estimating each one of these functions to be to be larger than theta I, so that these values are pretty high. Yeah, I'm going to go a little bit quicker over this. And this is something that looks like utility, right? So I give you a set of functions. You can think about these as G as good functions of X that I want to reveal. I want you uniformly bound the largest reconstruction error by delta. You can think about other variations about this. And just to make everything nice and convex, when I'm designing this mapping, I'm going to restrict X to have the same distribution as Y. This allows us to formulate that as a convex optimization problem. And then the goal is to try to design this mapping P of Y given X that does something like this. Right? So if you have this subspace of functions that are good, that you want to infer given X, and the subspace of functions that are bad, the secret functions, you want to somehow design this mapping so you attenuate, right, the space of bad functions, secret functions. You can already see that if the space spanned by private functions and the space spanned by useful functions are somewhat orthogonal, you will have a favorable trade-off between privacy and utility. In practice, that's not necessarily the case. What's going to happen is something like this. When you design that mapping, you're going to be increasing the MMSE of estimating both the secret and the private functions because there may be correlations between them. And and you can try to navigate this trade-off space under these restrictions by formulating an optimization problem. I'm not going to go into the details. I refer you to our latest paper. It's on arXiv on how to do this. Believe me, this is a convex optimization problem. If you knew the distribution of the data, you can plug it in and solve it. We have some numerical examples on that. But hopefully this just gives you a flavor of how you can use this interpretation of the principal inertial components to do this kind of subspace alignment and design these mappings. So I'm going to conclude just talking a little bit about, in practice, how can you estimate these principal inertial components from data, right, for especially very large data sets. I'm going to, just for 30 seconds, go over this part. What we have, in order to design use this PIC-based convex program, you have something that looks like context-aware privacy, where you have a reference data set. You can estimate P of S given X. You have your utility privacy constraints. You plug it into this convex optimization problem, give it to a convex solver, and it will give you a privacy assuring mapping. And as you sample new samples from P of X, you pass it through that locally through that mapping and reveal the sanitized Y. Of course, since the reference data set has finite samples, you might ask, well, your privacy and utility guarantees might not match from train to test time. So what is the relation between the number of samples in this reference data set and the guarantees that you can provide here? Well, this is one result on this. Lalita will be presenting in the next talk, I think, a lot more about how these trade-offs work. So I'm not going to talk about that now. Now, what I want to talk about is how can we estimate the PICs over large data sets. So this is something I'm particularly excited about. So just bear with me at the end. So how can you estimate these principal inertial components? Right. Well, there is one method of doing it. I already mentioned about it called correspondence analysis. This is a method in statistics where you build, if everything is nice and discrete, you build this contingency table, you normalize it, and you take its singular value decomposition, and you find the principal functions. There are a few limitations for this approach. First, it requires categorical data, and it does not really scale for large alphabets. These matrices will be really, really, really large. And there are other methods, such as the ACE method, that run into similar problems. So let's say that X and Y are continuous, or X is an image, or something like that. How can you scale this up to estimate the principal inertial components? In order to do that, you have to go back to the basics. Remember that we saw that the PICs are actually the solution of this problem of maximizing correlation, right? They're the natural solution of this problem where you're trying to maximize the correlation between F and X. And the problem of solving this up, so if now is a good time to pay attention if you're if I lost you at one point, but the problem of solving, so get back in the game. So the problem of solving this maximization is challenging because you're maximizing over all possible real functions of X and Y, right? You're searching over this large space of functions. However, you could be able to approach this as long as you could index these functions and search over a large enough space. And fortunately, like Kamalik already hinted, over the last few years, we have very efficient methods of searching over large spaces of functions via neural networks. Right? So when I think about a neural network, when I think about the output of a neuron of a neural network, I think about that as a point, right? Because that little neuron is nothing more than a point in the space of finite variance functions of the input, right? So that's what that neuron represents, right? And as long as it has finite variance, and which for all practical purposes, we can assume that is the case. So we can index the functions of finite variance, some functions of x through a neural network, do the same thing with y. And as long as we can cleverly design a loss function that we can backpropagate on and maximizes this correlation, we might be able to recover the PICs. And we actually did that. This is the loss function that we backpropagate on. It's something that also appeared in a paper called Deep Canonical Correlation Analysis, even though the authors didn't connect it to this theoretical machinery that we're mentioning here. And I just want to give you a flavor of how this looks on actual data. So this is something that looks complicated. It's estimating correlations over batches of your training data, but you can backpropagate this on TensorFlow, so you can actually fit neural networks to do that. Let's see how this works. So when x and y are jointly Gaussian, your principal functions are your neighborhood friends, the Hermite polynomials. And you can actually feed to two neural networks jointly Gaussian random variables, train them, and see that the output of these neural networks, after you normalize it, actually correspond to the Hermite polynomials. And this approximation becomes increasingly worse as you go to higher degrees because the PICs become smaller and smaller. You can repeat the same exercise using uniform bits. This is something.
You mean dimensions of the Gaussian?
No. When you go higher order polynomials in your basis. So when x and y are binary or bits, we looked at the binary symmetric channel case earlier. I mentioned that the principal functions are the parity bits, and you can also see that in this case, you approximately recover the parity bits here. And it's interesting because you can feed x and y through a binary symmetric channel with crossover probability 0.1, and it finds these associations. And you can change the bit and finds associations as well. And the cool thing is that now you can use this statistical technique called correspondence analysis at a scale that I think it hadn't been done before. Right? So correspondence analysis, what it sought to do is something that looks like nonlinear PCA. So you would find these principal functions, right? These gives you nonlinear dimensions of x, and you would get samples from your data set x and plot it according to these orthogonal directions. Then you will get samples of y and put on the same plot the orthogonal directions g1 of y and g2 of y and plot them together and try to find correlations between them. And before clustering, that's one of the applications of correspondence analysis, but these are nonlinear transformations, right? And unlike RHKS, you don't have to a priori choose a kernel here. You just train your neural networks. We can do that with fairly large data sets. This is one example with, I don't think you can read it properly, but this is the Kaggle food competition data set from Yumli. These are 50,000 recipes that we're doing correspondence analysis on. And here cuisine is x, cuisine is y, and x are your ingredients or your recipes. And you can plot them together in the same plot. And you can see that over here in this corner, you can't read it, but you have Asian cuisines together. Here you have European cuisines. Mexican is down here. And you can see associations between, like, for example, soy and sesame. They're close to the Asian cuisines. Brazilian cuisine is right in the middle, so that was something that I'm Brazilian, so I was pretty pleased with that. We recently had a paper at the NeurIPS workshop on machine learning for the developing world, where we applied this tool to analyze the expenditure of Brazilian congressmen. So Brazil has a very good open data program where you can go back to 2009 and see all the expense reports from the congressmen, how they're using their discretionary funds. And you can plot that and analyze it using correspondence analysis. And since I think this is being recorded, that's the last thing I'm going to say about that. And just to show that you can use this, do this at a much larger scale, we have results with Cypher 10 and Cypher 100 and your image sets that you usually care about. Of course, here correspondence analysis doesn't really reveal a lot of intuition, but at least just to show that this method scales.
Well, I would think it reveals that what are the overlapping features in these images, right?
Well, but the problem here, like, why are your labels? So you will end up just doing classification as usual. But this is just to show that, yeah, you can use this in data sets of the size that you care about.
Are you still
learning privacy, or are you now using the privacy tool sets to do?
So that's what we're working on now. Like, so that's a question of how can we then. This is not privacy yet. Like, hopefully, what we're trying to work on now is to get this and feed it back to privacy, and then these intuitions that we have from the information theory and from these optimization problems of filling subspaces, and now we can estimate these things. How can we present privacy mappings based on that?
A congressman that's going this privacy route, like what data would you
No,
release?
that's just pure. This is just pure data analytics. So I'm going to conclude with the same slide I finished yesterday. With big data comes big responsibility, a little bit cheesy, but I do believe information theory can help. And in things like privacy, fairness, and transparency, there's a lot of exciting work and a lot of theory that we can bring to this table. So again, this is just a few papers that my group has produced over the past couple of years. And yeah, I would be happy to take questions. Thank you.
We're about 20 minutes delayed. 1 minute for question.
Wait, do we have a break or no?
We have a break now, and then we'll take a 7-minute break.
I already asked about, but it's okay, I guess if someone else has a question.
Yes.
I guess I have a more of a general question. I actually really like this because I'm a statistician, so I appreciate looking a lot of this through a lens of especially conditional distributions and information. But when you do your literature search, do you ever actually look into statistical literature on data confidentiality and data privacy? Even though we have shifted and many of the methods were not formal, the ideas that you are talking about here have been explored in statistical disclosure limitation literature.
Yes.
And I often don't see any of that stuff referenced in CS papers or information. So I'm just curious as to, are you not finding these papers, or is it that somehow it doesn't relate, you feel, or what is it that it's missing?
So I can give you an answer for that. I'm always searching for those papers.
Yeah.
Like, for example, I can tell you my experience in working with these quantities, the principal inertial components.
Sure.
Like, because this is something that I came across it in the more correspondence analysis literature. And then learned that like information theorists had studied them, Rene had studied them, and so on.
Sure.
And then realized that statisticians such as Andreas Buja and so on had done phenomenal work on that. But these works don't reference each other, and they appeared over the space of several decades.
Sure.
So that's something that we're always trying to be as careful as possible. If you think there's any references that are missing, please let me know. I would be happy to.
And I'm not even talking about the general statistical literature. They have been paper in statistical disclosure limitation. For example, they use this idea of dimension reduction in a way, or there is a paper a while back, I think the methodology was called ROMM, R-O-M-M, randomized matrix, I don't know, something I can't remember, where they basically are looking at exactly like zero mean, minimum variance. You're looking at the principal components, and you're trying to break down the.
Were they looking at the spectrum of the conditional expectation operator?
I can't remember all the details.
Okay, so I'll definitely look that up.
I think another very interesting paper that does look at, and I wanted to mention this also to Camellica, maybe they were aware of this. There's a paper by Mario Trottini and Feinberg a while back, where they actually looked at the Bayesian perspective, like thinking about what are the limits of the adversary, and looking at these basically conditional type distributions and the limits, and some literature related to this. And there are actually many more other papers, but I mean, I can't remember all of it. I'm happy to take a look at a bit more carefully for you and point you at.
Absolutely, we should definitely chat. I think like once.
And I think there's a lot of novelty here, and I love the ideas, and even certainly some things that Camellica is talking about. But it seems that the SDC is being criticized often for not being formal enough. But it seems that some of the ideas that were initially introduced, even if informally, let's say, are being kind of completely ignored, right? And some of the ideas were there.
No, absolutely.
I think it's just,
You know, I mean, if you have a set of references, I would love to look them
sure,
up.
yeah.
Absolutely.
Partly my problem has been I do try to find them, but because these are like kind of disjoint,
Yeah, of course.
it's hard to
Yeah.
find them through foreign
Yeah.
references. And I really apologize. It is, you know, yeah. If you tell me, I will read them, or I will make Joseph read them.
And I echo that absolutely. Like something we're always striving for, because the language that like computer scientists, information theorists, statisticians use is like it's all probability and conditional probability and so on. And so a lot of these ideas appear in different forms in all these different fields, and we absolutely want to be as fair as possible citing, and so do send in.
Even some of these ideas of, I mean, this utility trade-off,
That is very old, I mean.
that is
Yeah.
very old, right? And
Yeah.
people
I
have
mean, it goes
discussed
back-
the boundaries, and you know, I don't, and again, I don't remember all, there's a lot
Yeah.
of different papers, but it's a very old concept, and thinking about the boundaries, even thinking about it geometrically. That said, the literature also, I know it's not as obvious, it is
Yeah.
easy, and it's not to say that, you know, statisticians as well, often, like, we miss a lot of other relevant literature when we work on stuff, so this is not directed one way, I just,
Yeah, absolutely. I think we spend, and I know my graduate students as well, probably a lot of people here have the same experience, that you spend a lot of time trying to find the right combination of keywords that you put on a Google Scholar search. You see, and sometimes we miss stuff. And absolutely, but if you have anything, please do send it to us, because we would absolutely include them.
Great outcome of this whole workshop to have a page where.
Actually, yeah, that would be fantastic. Like,
We would love to read them and follow up.
yeah. And again, some of them definitely do miss more of a formal treatment. But as I said, even if perhaps the credit or or maybe you will find some of the ideas relevant and interesting, and you can follow through.
absolutely, and I think
Died off and haven't been considered. Right?
absolutely, yeah, absolutely. Thank you so much for that.
Otherwise, it's great. I love it.
Thanks.
Thanks.
Thank you.
Any other questions, or yeah?
A really small comment. So I think this is really cool. It's very MMSE, you know, in its formulation, and I feel like at the end of the day, like the things that are really secret, like the really sensitive quantities, are all discrete. Like the point of examples are usually like your point of example is like, you know, political affiliation, right? So I guess it's just a comment, I guess, that like, you know, it seems like maybe it's I mean, you got some with, you know, binary examples and so on, whatever, but maybe like focusing more on like discrete examples of things you're trying to hide might be more applicable to like the applications you started with.
Yeah, yeah, for sure. Like when you have one bit, then an MMSE is probability of correct guessing. But yeah, no, absolutely. Like but I think that's absolutely correct. This is a.
Like the whole room would actually disagree with me on my premise that like.
No, I think it's.
Like the secrets are usually discrete. Like that's the key assumption of maximal leak exactly. The S is always discrete, so you can talk about guessing that.
Yeah.
But I mean, there are things like locational privacy and so on, where, you know, people would argue the quantity of interest is continuous. But you know, to me, it's like the location itself is not usually what people are trying to protect. It's like, you know, some discrete quantity that's sort of correlated with your location that you're ultimately trying to protect. So in the end, it always seems to come back to like discrete quantities that we're trying to protect. Yeah.
But it raises a very interesting question, which maybe I brought up with you. What is an upper bound on accuracy that an adversary should learn it with? Should it be 0, that you should never learn anything, or can you learn maybe with some 20% accuracy?
I guess a related question, discrete is like probability error predicting something, right? Versus continuous could be L1 norm or L2 norm of predicting something. You know, you might imagine making a case for either one. Like, let's say my salary shouldn't be predicted with L1 norm.
But it's stored in very discrete ways.
Well, you could discretize it,
So you
right? You
can
can say, okay, if it's
theoretical
like,
mostly.
it's all by dollars, so if it's like 20 bins left to the right of my salary, then I'm okay, or something like that. I think that's actually, I was reading your paper, and I would think that's the same thing. Like, maybe it's all the same, maybe you define it right.
So, okay, so.
Salary is a good example, actually.
Yeah, salary or height,
Quantity.
weights, and glucose
Well,
levels,
height-
that kind of stuff. Like
I mean,
maybe some medical data.
Anyone who just sees me on the street has my height already.
Right, I guess
salary maybe.
maybe medical data, like a blood pressure. If you're in the range, I can discriminate you on insurance. Maybe I don't want to be seen like my blood pressure like within a certain range. And you could discretize it
Is
first.
it really my blood pressure that I want to hide, or is it whether I'm diabetic or not?
Exactly. So if you hide blood pressure, that's continuous. But if you pre-discretize it saying I'm diabetic or not, then you hide that, and so that's another debate.
So I will probably argue, since you want an argument. So it is true that secrets are discrete, but a lot of the times, based on the continuous, it's very hard to predict the discrete, right? Like, you know, I mean, the blood pressure diabetic is probably a good example where you can. But, you know, like gender, right? It's based on, let's say, image gender, it's not easy to detect, right? So I guess, I mean, in theory, you're absolutely right. In practice, automatically figuring it out is probably...
You're saying like pre-discretization is not so easy.
Exactly, exactly. Rediscretization.
Like facial features or body
I'd say
type.
more than that, or sort of continuing this idea, we have continuous data. Secrets are discrete, but we can't necessarily know in advance which discrete secrets we want to protect down the line. And so pre-discretization only protects you for the secrets you can anticipate, potentially, and not for the ones you can't. And that would be an argument against focusing really on this
So what
binary.
is pre-discretization?
Meaning, so let's predict the secret based on this continuous variable, and then let's protect that binary variable.
Oh, okay.
But that, so that's a great idea if you know exactly what is the function of the continuous data that you're concerned about.
Yeah.
But if you don't actually know, because you don't know in 5 years what people are going to be caring about hiding, then you can't do it.
So I'll ask a loaded question then. If I can protect all hidden discrete quantities, then are we safe?
So actually, what I was going to say is that it seems like the notions of secrecy and privacy that have historically been most successful are ones that are like actually end up being as independent as possible of the structure of the thing you're trying to hide, right? So, a good example is like if you're hiding all possible binary valued functions of some random variable, that's sort of like, that's some total variation style guarantee, and you can interpret it in a continuous way, or you can interpret it as like binary things, but it somehow like has lots of operational meanings. And this came up in your talk yesterday. You were saying like, oh, well, you could consider different types of guessing, right? Rather than just trying to guess the secret, you could try to guess something close to it, or guess a set of k things, and you win if you get it in your first k guesses, or stuff like that. And any of these lead to the same definition. That's like a very robust statement, and like we tend to gravitate over time to things that have that type of robustness, right? So I would say like try not to bake the structure of the secret in, and try to look for things that are as independent as possible, partly for the reasons that Katrina said, that who knows down the line.
But I think the setup that Carmelita had, like if you're thinking about settings where you have explicit data user agreements, and perhaps there is no outside some kind of data sharing, and there's some additional restrictions, maybe there you could try to think about in order to perhaps gain more utility or something like that. But that's a very, very specific setting. I mean, and certainly will not, protect if you anticipate that it's going to go further out at some point, right? Which I think it is hard. I mean, this is why DP has been of the idea that you're preventing against the future attacks in a way, right? So.
No, I mean, if you can do it with good utility, that's... I think
that's the bottom line.
Yeah, of course, yeah.
So,
There's also the point that, yes, societal norms change, but it takes about a decade or, multiple decades. It wouldn't happen on a scale of like a few weeks, right?
It's not societal norms necessarily, though. We realize next week that the combination of these variables lets us predict something about you that we didn't know. These things are changing very rapidly.
No, we're talking about defining secrets, right?
Yeah, but so what the sensitive data about you is going to be different next week when we realize that we can infer something totally embarrassing from 3 things that currently seem innocuous. And I don't think it's just about norms. I think it's about what we know how to infer and that's changing quickly.
What other sources of data?
Yeah, outside
like if you
sources
look
of data,
sort of
yeah.
historically at how people have tried to classify sensitive versus non-sensitive information, it's often in terms of, oh, well, this is sensitive because it can be linked to these other data sets, and this is non-sensitive because it doesn't exist anywhere else, or it's, you know, surely it's okay to release, or whatever, you know, whatever kind of. It's not that there's always a deep engagement with social norms when you're thinking through like what's sensitive and not, right?
And I think these sort of exercises are doomed to fail. It's sort of like, let's decide that these are the, you know, the secrets.
I don't know. I think if your data had a very finite time, and if absolutely utility mattered, either you publish or you don't publish at all. Would you rather publish with some guarantees than none, or are you going to sit there and insist that it has to be very strong? I don't know. I mean, this could be a very critical thing.
Yeah,
I mean, I also think it depends to some extent on the applications.
I agree with you, but
I mean, you know, I think because I think whenever we talk about privacy, we are implicitly talking data release, but which may not be the case, right? So an example would be, you know, in location privacy, you are showing somebody some ad based on their approximate location, but, you know, you're not really storing what they're showing, right? So in that case, the fact that it will be used and linked 10 years later, you know, that's not right. So I don't know, I mean, I feel like these are all application dependent.
Yeah.
And I think utility also comes into play, right? Like if you're releasing your data now, it's because you want to get something out of it. Like and something will be correlated with my data, right? So somehow that has to come into account as well. So yeah.
But there's also one thing here I'd like to clarify. So Kamalika, you said local DP is broken and needs to be fixed. And perhaps the statement is correct on some level, but there's been some recent research that uses things like shuffling the data before.
I'm aware of that. Yeah.
Things like that, using secure aggregation, some cryptographic premises in order to collect data from people without even knowing who's sending you what, and you only see aggregates, for instance.
Right.
Secret sharing, things like that, to
I'm
move
aware
from
of
local DP to central DP. So there is some, you know, process that's.
Sure.
But the point is then there is some pre-processing needed to give privacy assurance.
There's some price, of course.
Right? I think somehow these pre-processing methods are not being taken into account in the larger context. To make it seem that it's all really shouldn't be context aware is somewhat naive, because a lot of time the data is being used to appropriately figure out where to add the privacy in any application. And so implicit in there is then the discussion that, oh, the data could be really bad, but I'm going to massage it to be reasonable enough to add privacy notions to it that are strong enough. So then there's already an implicit pre-processing that is happening that's not being accounted for in the end-to-end. So the application's coming into play, is all I'm saying. All right, we'll take a 5-minute break.
Thanks, everyone.